Okay, thank you. So welcome to the last talk of this session before lunch. It's a great pleasure to have Vivek Rai from ISER Pune. We'll talk on, title of his talk is Towards a Mod P Lubin Tate Theory for GL2 over totally real fields. Over to you.
Thank you, Mahesh. And thanks for the organizers for organizing this two-day conference. Okay, so this is a joint work with Debargha Banerjee. So let's directly dive in. So what the talk is about. So the aim of the talk is to show that the mod P local Langlands correspondence for a totally real field can be realized in the mod P cohomology of Lubin Tate towers. So in this lecture, there'll be a lot of different flavors of local Langlands correspondence, which I'll mention, which I'll clarify as we go on. So this is the primary aim, and so we are motivated to prove such a result because of the following result of Chojecki. So what he showed is, so you start with a continuous irreducible Galva representation, which is odd. So in this case, it's going to be modular because of like conjectural proof. Anyway, so this is the condition on rho, and you assume that rho P, which is if you restrict rho to the.
Sorry, are you changing the slides, Vivek?
Yeah.
We can't see the.
We can't see the changes. Yeah,
oh, so. Okay. Still no, you can't see it.
No. It isn't
Vivek,
still in the first.
You can unshare and share again. Maybe there is some problem.
So it's saying the sharing is paused. Bring your shared event to the front.
Correct. So yeah, just for safety, you can unshare again, share again, and then we'll check.
Okay, so I'm stopped. So I'll stop the share now.
Yeah.
Okay.
You can share again.
Yeah. Let me do that. So. So I'm changing the slides now. Can you see?
Yes.
Yeah, now it's fine. So you keep the PDF open. Don't minimize or anything. Then it will be fine.
Okay. So you can see the change right now. Okay. Is it
yes.
right?
Yeah.
Okay. Great. Thanks. So okay. So let me just start again from the beginning. Sorry for that. So okay. So the aim of the talk is I've mentioned is to show that the mod P local Langlands correspondence can be realized in the mod P cohomology Lubin Tate towers. And the motivation for us to prove such a result came from a result of Chojecki. So he showed that if you start with a Galva representation, which is continuous, irreducible, and odd, and you further assume that if you restrict this global representation to the absolute Galva group of QP, if this is irreducible, then you have a injection, which is GQ cross GL2 QP equivariant injection. So rho appearing here is the one which you started with, and this pi actually is a representation of GL2 QP, and this comes from the mod P local Langlands correspondence for GL2 QP. Since you're assuming that this rho P is irreducible, so we know that this pi has to be supersingular representation. Okay, so and this injects into the Lubin cohomology of Lubin Tate tower. Okay, so this was the motivation, and we wanted to generalize this thing for the case of to the case of totally real field. So that means that instead of looking at Q, we'll be looking at F. Okay, so this is okay. So we generalize above result to the case of totally real field, and to just before stating our main theorem, we'll just define few notations. So let F be a totally real field of degree D. So you fix a rational prime P, and you also fix a prime of F which lies above P, match track P. Let GF denote the Galva group of absolute Galva group of F, and for any finite place V of F, FV will denote the completion of F at V. And yeah, okay. So this D is a coordinate algebra over F, which we demand that it splits at exactly one real place, and it has to be non-split at all the other real places. So this is the coordinate algebra we'll be using to define Shimura curves. Yeah. And another condition we impose is, not just that, at also the place P, the coordinate algebra D is split. Okay, so it means that D tensor with FP is a set of matrices. Okay, so the main result is the following. So again, we are starting with the same conditions on rho. So let rho be representation of GF to GL to FP bar, which is continuous, irreducible, and totally odd. And again, you impose the condition that locally at the place P, if you restrict it to Galois group of QP bar over FP, it is irreducible. Okay, so same assumption as Chojecki's results. Then, assuming a famous conjecture of Buzzard, Diamond, and Jarvis, so we have a injection which is GF, GL2, FP cross a finite product. So this product varies over, some set sigma minus sigma prime, which will be until later. But this set is finite. Okay, so there are only finitely many components here, and we have an injection like this. So rho tensor pi p tensor this pi w, it injects into the supersingular cohomology of the Shimura curve, which we again will define later. And since because of the restriction that, our assumption that rho p is irreducible, so conjecturally rho p should correspond to a supersingular representation of GL2 of FP. So that is pi p. Okay, so pi p corresponds to rho p under the conjectural mod p local Langlands correspondence for GL2 FP, and K is some specific level, which again, will be discussed later.
Sorry, but can I interrupt?
Yeah.
There is no canonical pi p, right?
There is no canonical, exactly. There's no canonical pi p, but the point is that it is assumed that, so it has to be supersingular, right? So
but
assuming
which supersingular?
So that we are not concerned with. So assuming that, if there's such a conjectural mod p LLC for GL2 FP, I'm just taking that particular pi p. If it is established, then I'm just taking that pi p. So we only need the condition that pi p has to be supersingular. We don't need which one, but we just need that. So if rho p is irreducible, so this is so it's at least this pi p is supersingular is what people assume, right? It has to be supersingular.
Okay, so I think one of pi p is constructed by Broglie and Pascuna in their paper.
Yeah. So right. So the point is not which pi p I'm taking. The point is that whatever it is supersingular representation of GL2 FP. Does it answer your question?
Not really, but okay, you can go on.
Okay. All right. So right, and K is some specific compact open subgroup. So we have this first injection, and furthermore, if you assume a Serre type conjecture, then we have the same injection, as in the left hand side is the same, but it injects into the limited cohomology. Okay, so there are two things going on. So if you assume Buzzard diamond Jarvis conjecture, we have the first injection inside the supersingular cohomology, and assuming another conjecture, we have an injection into the limited cohomology. But the point is, let's call the first injection as the first step, and the second as the second step. So okay, so the first step is where the most of the work was done. The second step actually follows from the definition, and most of the work for the second step was done by Carryhold. So the first step is to show that
did you say what pi w was? I missed it, I think.
Yeah, I did not say that. So these pi w are representation of D tensor over F of FW times. So you're considering the units of D tensor FW. So pi w is representation of that.
Okay.
Yeah, so these things would come towards the later when I exactly state what this conjecture is, Buzzard diamond Jarvis conjecture. Okay, so the first step is to show that the mod p local Langlands correspondence can be realized in the mod p cohomology of supersingular locus. And as I said, this is where we did most of the work. The second step is to show that the mod P cohomology of this supersingular cohomology Shimura curve injects into the mod P cohomology Lubin-Tate towers. So by this I mean that, so once we establish the first step, the second step is just to show that the right hand side of this H1 FP, SS stands for supersingular, by the way. Okay, so this H1 FP, this injects into H1 hat LT. So the main thing is to get step one, is to prove step one. Okay, and so we'll be spending most of the talk to prove the first step, and there'll be no mention of Lubin-Tate towers at all. Okay, so the strategy of the proof, we closely follow the strategy of Powitsky, but there's one crucial difference in the proof of the first step, which I'll mention towards the end this time. Okay, so some basic about Shimura curves. So few more notations. So FP denote the completion of F at P, OPB is ring of integers, and K be the residue field of OP. Let AF be the finite ideals of F, and G be the restriction of scalars from F to Q of units of D. So, indexed by the compact open subgroup K. So if you take any compact open subgroup K of the finite idyllic points of G, you can have like the following expression, which is actually a compact Riemann surface. And as you vary K, you will get a projective system of compact Riemann surfaces. So in this expression, you quotient on the left by the Q rational points of G, and on the right by the compact subgroup K. Okay. So in fact, Shimura defined a canonical model, which we denote by MKG, of these compact Riemann surfaces, such that if you take the complex points of MKG, we exactly get the above expression. Okay, so these models are defined over F, and these also constitute projective system of complete smooth algebraic curves over F. Okay, so few more notations. So okay, so let gamma be the restricted direct product of the units, which is of D tensor FB. Okay, and you take this product over all the finite places V not equal to P. And you define K to be K P power N times H, where H is a compact open subgroup of gamma. Okay, and KPN is given by, I mean, this set of all matrices, such that if you go mod P power N, it's identity. So essentially what I'm doing is that for any level K, I'm separating the P part and prime to P part, which is also called tame level. So H essentially is the tame level, and K P power N is it's a P level. Okay, and we denote MNH by this. So MNH means that I'm taking this level, Kp power N times H. Okay, so we are interested in the mod P reduction of Shimura curves. So it is necessary to work with its integral model. So Carriol has showed that for sufficiently small h, there exists integral model of MNH over OP, which we again denote by MNH. So unlike in the case of modular curves, this MNH does not have a modular description, but still we can define ordinary and supersingular points for the mod P reduction of the curve MNH. Okay, and so that's what we do next. Okay, so how we define these points on MNH? So let M bar NH be the mod P reduction of MNH, and let X be a geometric point. Then Carriol has attached to this point X an OP divisible module EX. Okay, and Drinfeld has actually given a classification of all such OP divisible modules EX, and we know that there are only two possibilities in this case. Okay, so in the first case, EX would look like sigma 1 times FP mod OP. In this case, we say that X is ordinary, or else it would be sigma 2, and in this case, we say it's supersingular. And by sigma, so sigma H is the unique formal OP module of height H. Okay, so depending on which one falls in which, we define X to be that kind of point. Okay, so let MNH ordinary be the set of all ordinary points of M bar NH. Okay, so you collect all the ordinary points of M bar NH. In fact, one has a further decomposition of this M bar ordinary NH in terms of disjoint curves, which I denote by M bar ordinary NH comma A, where A varies in this projective line, OP mod P power N. And one also knows that this GL2 OP mod P power N acts on these curves, and it actually permutes them. Okay. So, okay, so now what we want to do is that we want to pull back these ordinary and supersingular points to the characteristic 0, like to the curve MNH. So for that, what we do first is so let MNH and denote the analytification of MNH. So this step again, it's a technical requirement which I will mention towards the end why it's needed. Okay. So now let this be the reduction map pi from MNH and to M bar NH, and we define the ordinary and supersingular part of MNH by just pulling back by just pulling back the ordinary and supersingular parts we defined for the reduction. Okay. So we have a decomposition MNH and as in terms of ordinary as well as supersingular. As I mentioned earlier, that the action of this group GL2 OP mod P power N is such that it permutes these curves MNH comma A ordinary. Okay. So you let B be such a point in P1 of OP mod P power N, and Bn denote the Borel subgroup of upper triangular matrices. Okay, inside GL2 of OP mod P power N, which stabilize this particular part of ordinary curve. So in particular, so for A inside this we can also define this MNH ordinary A part by just pulling back again the mod P ordinary points. Hence, so this cohomology group, which is Ital cohomology group, which support on MNH ordinary, this could be a representation of Bn. Okay, that is because, as I said, that so Bn stabilizes MNH ordinary and BH. So this will also act on the Ital cohomology, which is H1, and so it would be a representation of Bn. And because of the decomposition, which is this decomposition of ordinary points, we can in fact write the cohomology of H1 MNH ordinary MNH in terms of as an induced representation from Bn to GL2 OP mod P power N. Okay. So the takeaway from the section on Shimura curves is that one can define supersingular and ordinary points for MNH. And the second thing is that the cohomology group, Ital cohomology group, H1 MNH ordinary, is written in such a way that it is induced from Borel. Okay, so I mean, if you just keep these 2 points in mind, I think it'll be all right for the next slides to follow. Okay, so next we will define the meaning of this complete cohomology of Shimura curves. So this notion was first introduced by Emerton. And so complete cohomology is interesting because conjecturally it says that it realizes the mod P local Langlands correspondence, which would be clear after we state the conjecture of Buzzard and Jarvis. In fact, Emerton has shown that the complete cohomology for modular curves realizes mod P local Langlands correspondence for GL2 QP. Okay. So the definition is as follows. So again, you start with the Shimura curve, okay, with level Kp times K upper P. And from now on, we assume that there's only one prime P of F which lies above the rational prime P. Then the definition of complete cohomology is given as follows. So what you do is that you take the direct limit over all these individual Ital cohomology group over K lower P. So K lower P, this varies. So these are compact open subgroup of GL2 of GL2 of FP. Okay. So that's why on the left hand side there is no. So there's only tame level. There is no P level. So this is the definition. And in fact, this cohomology group, it was shown by Emerton that it's nice in a way that it is admissible, and it also has a commuting action of the Galois group GF as well as smooth action of this GL2FP. Okay, so now we'll state Buzzard diamond Jarvis conjecture. So for that, we have to define Heike algebra and maximal ideal. So let's start doing that. So let U be an open compact subgroup of the units of DS. Okay, and again, we start with the Galois representation, which is irreducible, continuous, and totally odd. Same assumption as in a main theorem. And let sigma be the finite set of places of F such that either W divides P, or D is ramified at W, or rho is ramified at W, or GL2 of OFW is not contained in U. Okay, so we will denote by saying that this is a set of bad places which are finite. So for the finite places V of F at which these splits, which are, of course, all but finite, we define the Heike operators in the usual way, the double coset operators TV and SV, which are elements of endomorphisms of H1U SP bar. Okay. And we define the Heike algebra to be the commutative SP bar subalgebra of the endomorphisms. But there's a typo here. So this should be not SDU, this should be H1, H1U SP bar. It's our cohomology. Yeah, so generated by TV and SV for all V, which is not in sigma. Okay. Let rho be the maximal ideal of this Heike algebra, which is generated by the operators TV minus SV trace of rho from V and this norm V minus SV determinant of rho V. So this is the usual way you define the maximal ideal corresponding to rho. And we also define the torsion part of H1U FP bar. So embryo torsion part of H1U FP bar just means that you're taking all those F in H1U FP bar such that TF is equal to 0 for all T in embryo. So it's essentially embryo kills this F. And you define H1 FP bar embryo to be the direct limit over all U, okay? Over all U. So U was a compact open subgroup of DF star. So you vary all U and that you denote by H1 FP bar embryo. Okay, so the statement of the conjecture is follows. So let F be a totally real field and same assumptions on rho. Then the FP bar representation. Okay, so this is the big guy which is constructed out of taking direct limits. So H1 FP bar embryo, it's actually a isomorphic to a restricted tensor product of this rho and then pi W's, okay, where W varies over all the finite places of F, such that pi W is a smooth admissible representation of DW, units of DW. So this would answer the question of Mahesh. So if W does not divide P, okay, and if D splits at W, then of course, pi W is a representation of, first of all, of GL2 of FW, and it's actually corresponding to a representation attached to rho W by the modified mod L local Langlands correspondence. So what I mean is that, so suppose if W does not divide P and if D splits at W, so then this particular pi W is the one which corresponds to rho W under the modified modulo L local Langlands correspondence. And if this does not happen, then it's either one-dimensional or two-dimensional representation of DW. And there's another part to this conjecture which we don't use in this talk, but I'll just state it. So the first point was about when W does not divide P. Well, if W divides P, then first of all, the representation is non-zero, pi W. And then, this just tells the socle that the socle of the representation of pi W, okay? So this would be, yes, this is not needed at all, so I'll not explain what this means. Only the first point is what we're interested in. Okay, so a few comments about this conjecture. So it's actually a theorem in the case of modular curves. This was proved by Emerton. But when F is a totally real field not equal to Q, it's still a conjecture, mainly because mod P local Langlands correspondence has not been established for GL to L, where L is a finite extension of QP. So what Mihir was asking in the beginning, so like, there's no mod P local Langlands correspondence for GL to L, where L is a periodic field. So yeah, and yeah, another important thing is that in the above conjecture for finite places, W not dividing P, if D is placed, then pi W, okay, which is a mod P representation of G L2 FW. So first of all, this FW is not a periodic field, okay? It's an extension of some QL where L is not equal to P. So this is given by the modified model local Langlands correspondence by Emerton and Helm. So which we will recall now. So let P and L be two distinct primes, and so let GL2 E, in this case, E is an extension of QL, finite extension of QL. Okay. So so this mod P local modified mod P local Langlands correspondence. I mean, I'll not go through all these bullet points, but essentially I'll just say that the main thing is, so this Galois representation rho. Okay, so you have GE on the left, where E, as I said, is an extension of QL, and on the right, and these are representation like over FP bar. So there's P not equal to L situation. Okay. So in this case, the local Langlands correspondence has been established. Okay. And in fact, not just for GL2, in fact, it's established for GLN by Emerton and Helm. So we will just be using it for n equal to 2. Yeah, and so this just gives you all the possibilities, like if starting row, if rows looks like, let's say if it's not a twist of one direct some omega, then what is the corresponding pi row? So pi row is a representation of GL2 of E. Okay, so this gives all possibilities. I just put it for the sake of completeness. Okay, so far what you have just said is that, okay, so just to recall, so this conjecture is what we'll be using in a main theorem, and the main point is this. So this decomposition of H1 FP M row in terms of this restricted product is like this, and these pi W's are actually the one which is given by Emerton and Helm. Okay, when W does not divide P. Okay, so an important result is, so let pi be the mod P admissible representation of GL2E. Again, E is a L-adic field associated by the modified mod P local Langlands correspondence given by Emerton and Helm to this representation GE to GL2 FP bar. Then there exists an open compact subgroup K of GL2 of OE, such that if you take the K invariance of this pi, the dimension is just 1. Okay, so this would be an important result for the proof. And so to prove this proposition, we actually did the case-by-case analysis of the above modified mod P LLC, and we explicitly figured out what K should look like. Okay, so the proof of first step. So the starting point is this exact sequence, long exact sequence, and this is where yeah, so this is the reason why we have to do identification, because once you identify the Shimura curves M and H, then the set of supersingular points becomes an, so you can you have an open immersion from the supersingular points to M and H, and the ordinary points, set of ordinary points would be a closed immersion. So because of that, we would be having this long exact sequence. Okay, so this is the starting point. So taking direct limits over all compact open subgroup KP of GL2 FP in the above exact sequence, we get the following. So in the, okay, the top exact sequence, as you can see, there is M, N, H. Okay, so this N is the P part. So I'm taking direct limit over all such, P parts. So in the second exact long exact sequence, you can see there is no P part, and it's only the tame level. Okay, so if you take direct limit, you will get this exact sequence. And from this above exact sequence, let's break this long exact sequence at this H1 MKP and FP bar, okay, to get a short exact sequence like this, okay, where I mean this image of F1 is actually just H1 MKP ordinary by the kernel of F1, okay. So we get this short exact sequence from the above long exact sequence. Okay, so now let G denote GL to FP, and now we will be applying this Helm G pi p functor to the above short exact sequence, where pi p corresponds to rho p under the conjectural mod p local Langlands correspondence for GL to FP. Okay, so we'll be applying this Helm functor to this short exact sequence. Okay, so just plug in in place of image of F1, just plug in this isomorphism. So after doing that, we get this exact sequence. Since Helm is left exact, so it will remain injective. Okay, so you have this long exact sequence. Now, the important point is the following. Since pi p is supersingular representation, okay, we know from the definition of supersingular representation is that it cannot occur as a subquotient of any representation which is induced from Borel. Okay. Hence, the first term is actually just 0. Okay, so this Helm G pi p comma the first term, I mean this would be just 0 because pi p cannot occur as a subquotient. So in particular, it cannot occur as a Okay, so because the first term is 0, we get the following injection. Okay, so you can see this Helm G pi p. This injects into Helm G pi p image of F2, and this image of F2. I mean, I'll just go a couple of slides. So this F2, as you can see, this is a map. It is mapping into H1 MK upper P supersingular. So image of F2 is it's a subspace of H1 MKPSS, right? So what I'm doing is that I'm just replacing image of F2 here by the whole space. So obviously there's an injection here also. Okay, so now we take direct limit over all compact open subgroup K upper P, and now we will drop even that K upper P notation from these above sequence, and so we get the following injection like this. Okay. So taking embryo torsion, where embryo is the maximal ideal which was defined earlier, we have the following injection. And this is the place where now we'll use Buzzard Jarvis conjecture, okay? Because on the left-hand side, you can see this is H1 FP bar embryo. So this was exactly, let me just go back a couple of slides. Yeah, so this H1 FP bar embryo, right, this guy. So we will replace, we'll be using this conjecture at this point. So yeah, okay, so tensoring both sides by pi p over FP bar and using the conjecture, we have the following injection. Okay, since we are just tensoring over FP bar, so it's still an injection. So I'm replacing H1 FP bar embryo by rho tensor over restricted tensor product over all finite places pi w. Okay, so now we have an injection of rho tensor of this whole product inside this Helm space, because first of all, G is GL to SP, okay, and this G does not act on pi W's if W does not divide P, okay. So there's no action of G, so obviously there's an injection into the Helm space like this, and using the evaluation map. So okay, so what we're trying to do is that okay, so the last, just see the last injection, the right hand side of that. We'll be using evaluation map on this right hand side to say that this actually injects into H1 FP bar supersingular embryo, and this is because you define this evaluation map V comma F goes to F of V, and this is injection because pi p is irreducible. So if there's something in the kernel, then this whole map would be eventually 0, which cannot happen. Okay, so this evaluation map is in fact an injection, and hence we have the following injection. So, okay, so this the right hand side, because of evaluation map, this injects into H1 FP bar SS, right here, the right hand side of this, and the left hand side follows from the first statement which I said, that since G does not act on pi W if P does not divide W, you have an injection into the Helm space. Okay, so we have, okay, so now we have this injection, but the point is on the left hand side, still there are infinitely many terms, okay? Because pi W values were all finite places. So, but in the main theorem, there was, as I said, there was only finitely many pi Ws, okay? So we have to somehow eliminate or, yeah, eliminate all but finitely many pi Ws. So for that purpose, we will be using the the important result which I discussed earlier. So we have to choose some compact, some level. So how we are going to choose is that, so if W does not belong to that places, okay, so for that I'll take the whole of GL2OW. Okay, now for the bad places, I'm defining a subset of those bad places by sigma prime to be the bad places such that D splits at W. Okay, and define the level to be K sigma prime and K above K lower sigma prime and K upper sigma. Okay, now this K lower sigma prime, I'll be choosing these KWs according to the important proposition which yeah, this one. So it says that, right? So you can choose a compact open subgroup K such that dimension, if you look at the SP bar dimension, it will be just one. So I'll be using this proposition to choose those KWs. Yeah. So this is a way I'm defining this level. Now, if you take the K invariance in the above injection, as you can see, all but finitely many representations pi W will vanish, right? Because of bad places where W splits, the dimension is one. And for the good places, we know that if you take GL2OW invariance of pi W, it will again be of dimension one as a SP bar vector space. Okay, so this gives an injection into the supersingular cohomology, and this was the first step of the main theorem. So yeah, so I think I will stop here, but before that, I'll just mention a crucial difference between our result and Chojecki's result. So in the classical case of GL2QP, one knows that there is no non-trivial extension between principal series and supersingular representation. So that fact was exploited in his proof. But in the case of GL2E, where E is E is the extension of QP and not equal to QP. In that case, it is shown that under the assumption of Buzzard dimension conjecture, there are non-trivial extensions between supersingular and principal series. So we could not use his strategy in that regard. So that's the reason we have to work with this Helm spaces, as I've discussed here. Okay, so I think I'll stop here. Thank you.
Okay, thank you. So a round of applause for Vivek. We have a short break, so if there's a quick question or two.
Yeah, Mehir, maybe. So if is this still a like in the proof, I'm not using the exactly what pi p I'm using. I'm just using that it is supersingular. So which one?
Yeah, I understood.
Yeah. Okay.
But can you recover pi p from this H1 FP bar? Maybe H1 FP bar is too big.
Yeah, exactly. So the main motivation of Chojecki to do all these things was to actually get some information about this pi p from the Lubin cohomology. So that's the reason he showed that it can be realized in such a it can be realized inside this cohomology, but it's still a very big cohomology group. So yeah, we don't know how to recover that. Yeah.
Okay, thanks.
All right, let's thank all the speakers of this session, and we'll resume after lunch at 2 o'clock.